All right, Chapter 32 is called Faraday's Law, and it involves electromagnetic induction. And I know we don't know anything yet about electromagnetic induction, but that's what this chapter is going to teach us, so let's get started. Well, we already know, as I have stated here, that moving Q's electricity makes B field magnetism. So electricity makes magnetism. Well, as we already know to some extent, nature loves symmetry, and in 1831, Michael Faraday in England and concurrently in the United States, Joseph Henry discovered how to use magnetic fields to produce electricity. And as I have here, and please get this into your notes because this is an historical moment in time, because it ushered in the age of modern-day electricity. This concept of electromagnetic induction developed into those spinning wire coils that we call turbines, where we can spin those wire coils in these magnetic fields, and electricity is made that ultimately was developed into the electrical grid and system that we use to power our homes. So let's understand a little bit more about what Faraday and Joseph Henry discovered. So what they saw was that if you took a permanent magnet, so as I have here, if you take a permanent magnet and you just move it around a wire. Now, the wire is just a wire. It's a loop in this case, so this circle here is our wire. I have it connected to an ammeter, but it's not a powered device. The ammeter is passive. It will just measure whether there's current in that circuit, so the needle deflects if current appears in that wire, but there's no power supply. What Faraday saw was that if you moved the magnet, now the example I have here is that we're taking a permanent magnet and taking the north pole of the magnet and just moving it upwards towards the coil, so the motion is upwards. The area of the coil, so this pink area and that pink n-hat vector, which we'll get back to later in this chapter, is seeing stronger B field values through that cross-sectional area. So as the magnet is moved up, points here, right, are seeing stronger B field values. Well, as it turns out, what we are going to keep in mind is that nature is going to fight for the status quo. Nature is going to try to keep that B field from getting stronger by making what is called an induced B field from an induced current. So the electrons in the coil feel the changing B field getting stronger, and it wants to keep that from happening. So it is going to make a current. Now I know we don't know why yet, so we'll talk more about exactly what's going on as we go through this chapter. But it's going to make a current, which we call the induced current, which produces an induced B field, in this case downward, to act against the increasing B field. Now, the induced B field and the induced current is a lagging effect. So it will never just cut off the changing B field. First, the B field begins to get stronger. Induced current, induced B field, try to fight that effect, but it's always lagging. Okay. Then the only other thing from our introductory kind of notion here, which again, we're really not into a full understanding of induction and what is going on. It's just introducing this notion, this example of this is what happens as the B field changes through that area, is first of all to understand that it's the B field and the area that's important, namely the magnetic flux through that coil area, that is going to turn out to be mathematically significant to us in calculating the induced effect, the current that's produced. Also, what will be very important, I don't want to skip over it entirely, is that it is definitely the relative motion between the loop and the magnet. So for the example we just talked about over here, instead of moving the magnet toward the loop, we could let the loop fall down and move towards the magnet. We would get that same effect, the increasing B field and the induced current going in the direction clockwise here to create that downward induced B field. Now, the one thing that is really important in terms of your getting conceptual multiple choice type of questions correct is to absolutely note it isn't just the value of the flux, right, that it's strong or weak. You can have an enormous magnetic flux value through a coil, but have no induced effect. It is the changing, the time rate of change of that magnetic flux, as we're going to see when we introduce it more formally in our coming lessons, that results in the induced current. So flux alone does not do it. It has to be changing magnetic flux. So there's our introductory page. I realize that at this point we don't have a deep understanding or much of an understanding of exactly what is going on, but we need to introduce this notion of induction and just the experimental result that this is what happens.